.3 Doing Chemistry. Observation and Reasoning. Malaria has deeply shaped human culture. It has plagued mankind since ancient times. Chinese emperors, Egyptian pharaohs, citizens of the Roman Empire, and even George Washington all had malaria. It may have determined the outcome of wars and the decline of empires. But what causes malaria? It wasn't until the 1800s that scientists began to make discoveries about how people are infected with malaria. Answering a scientific question like this begins with observation. How do chemists solve problems? We use our senses to collect data or information about the world, but sometimes our senses need a little help. Scientific tools like telescopes, microscopes, or mini video cameras, such as those used in arthroscopy, extend our ability to collect data about the world. This data can be in the form of numbers determined through measuring, called quantitative data, but it can also be in the form of words used to describe something, qualitative data. After obtaining data, scientists use models and reasoning to make connections and explain the data. Deductive reasoning proceeds from general statements, called premises, to a specific conclusion. Inductive reasoning proceeds from known data to an unknown general conclusion. It uses facts or data to draw general conclusions, but it cannot prove these conclusions to be completely certain. Instead, it shows only the probability that a conclusion is true on the basis of the evidence under consideration. Most scientific conclusions are based on data, so they use inductive reasoning, but deduction also plays a part. Let's look at some examples and see whether you can figure out which type of reasoning is being used. Questions. What is the difference between a theory and a law? How is scientific inquiry done? What should a scientific question look like? What are some examples of scientific inquiry? Terms: quantitative data, qualitative data, hypothesis, scientific inquiry, theory, law. Example 1-to-1. Identifying types of reasoning. Reasoning. Determine whether the following arguments use deductive or inductive reasoning. A. When potassium chloride, sodium chloride, magnesium chloride, or calcium chloride is mixed in water, it dissolves readily. Because barium chloride is a similar salt, it also should dissolve in water. B. Any substance that floats on top of water has a lower density than water. Vegetable oil floats on top of water. Therefore, vegetable oil is less dense than water. Solution. This argument attempts to show that the conclusion is probable or most likely based on similar situations, but it cannot prove that this salt or any other salt will dissolve in the same manner. Therefore, the argument uses inductive reasoning. As an example, silver chloride is an insoluble salt, showing that inductive reasoning is not completely conclusive. B. This argument compares premises and arrives at a conclusion that must be true if the premises are true. Therefore, the argument uses deductive reasoning. Sir Ronald Ross, a British doctor, used reasoning to learn about how people get malaria. He grew up in India, an area of the world where malaria is widespread. His grandfather contracted the disease when Ross was a child, and Ross purposed to fight malaria when he grew older. He studied it in the late 1800s, connecting malaria to mosquitoes after deliberately exposing uninfected mosquitoes to a malaria patient and then finding the malaria parasite in the mosquito's intestines. This led to a new approach to fighting malaria, controlling mosquito populations. We use this approach in the fight to eradicate malaria today. Scientific inquiry. When you think of scientists, you probably picture people in a laboratory performing experiments. Scientific inquiry actually starts with what many consider to be in the middle of the process: observation. After a scientist makes an observation, he may recognize that there is a scientific problem or question that needs answering. He may then do some initial research to determine what is already known about the problem and what investigations others have done on it. On the basis of his research, He may then develop a suggested explanation for the scientific question. This suggested explanation is called a hypothesis, and it should be as simple as possible. It should be reasonably based on current scientific models related to what is being studied. Most importantly, it must be testable. Testing hypotheses about currently observable phenomena is referred to as operational science. Confirming the effectiveness of a new vaccine is an example of operational science. Hypotheses regarding phenomena that occurred in the unobservable past are part of historical science. A good example of historical science is a hypothesis regarding the origins of matter. Both creationists and naturalists have ideas and beliefs about how matter came into being. But the actual origin of matter is an event that happened in the past and cannot be repeated. It is therefore outside the realm of operational science. After defining a hypothesis, scientists then collect data to test the hypothesis. Some people think that this is done only in a laboratory, but in reality, scientists gather data in many different ways and in a variety of locations, often outdoors, called field research or fieldwork. Scientists next use reasoning to analyze data that they have collected. The analysis is used to evaluate the hypothesis and to form a conclusion as to whether the data supports or refutes the hypothesis. In the event that the data refutes a hypothesis, all is not lost. The scientist may then modify the hypothesis. Sometimes, though, the data will suggest that a hypothesis needs to be discarded and replaced by a new one. This process of identifying a problem or question, forming a hypothesis, collecting and evaluating the results is collectively referred to as scientific inquiry. This may be more familiar to you as the scientific method. This method is usually taught in a very linear way, with students running a set of steps to rigidly follow. In reality, the scientific process is much less rigid and linear. In fact, it is cyclical, since numerous instances of refining prior work tasks to modify, update, or refine them, or perhaps even start over. Experimentation. Experiments are a major part of scientific inquiry. They rely on a simple, reasonable, testable hypothesis. An experiment is a way to observe a natural process, sometimes under controlled conditions, so that a scientist can know whether her hypothesis is right or wrong. Experiments are an important part of the model-making process. In a controlled experiment, only one condition changes at a time, so that a scientist can isolate its effect on the experiment's outcome. The different factors that change are called variables. The scientist changes one of these variables, called the independent variable. This can generate changes in other factors that she did not directly cause. These are called dependent variables. The group of samples exposed to the independent variable is the experimental group. The group of samples not exposed to the variable is called the control group. What a scientist observes or determines using data gathered from an experiment is said to be empirical. A key element of scientific inquiry is repetition. To arrive at the best possible conclusions with the least uncertainty, scientists repeat experiments using multiple samples called trials. Each trial provides more data. A single trial that yields data that supports a hypothesis is not as conclusive as hundreds or perhaps even thousands of trials that produce the same results. Confused by all these terms? Don't worry. Read the example below to help you sort out how scientists use them. Example 1 to 2. A controlled experiment. Case study. Experiment in orbit. One of the questions that NASA has explored aboard the International Space Station is how plants grow in the absence of gravity. In a microgravity environment like space, how do plants know which way is up or down? In one particular experiment, scientists used magnets on flax seeds in zero gravity to see whether magnetism affected the direction of plant growth. They hypothesized that if certain slightly magnetic parts of a plant called starch grains were exposed to a highly magnetic environment, then the starch grains would move along the magnetic field lines. This movement could control the direction in which the roots grow. Here's an example of how they might have set up their experiment. A group of 50 seeds could be grown in the dark while in orbit around the Earth. They could be subjected to strong magnetic fields, but because they would be in orbit, they would not experience gravity. Another group of 50 seeds could be grown under these same conditions, but without the magnetic fields. Now suppose that after the seeds sprout, root growth in 42 plants from the first group seems to follow magnetic lines. The rest of them either have no recognizable pattern in their root growth or do not germinate. The scientists could conclude that the starch grains do help plants know which way is down in this case, though there might be other factors at work. Using the information from the scenario just described, identify the independent variable, dependent variable, experimental group, and control group. Then check your answers below. Solution. The independent variable is the magnetic environment. The dependent variable is the direction of root growth. The experimental group is the 50 seeds subjected to the strong magnetic fields. And the control group is the 50 seeds grown without the magnetic fields. Hypotheses are sometimes tested using an experiment in which scientists cannot control the conditions. These are called natural experiments. In natural experiments, scientists usually try to determine what variables are interacting, even though they cannot control them. Research in ecology, meteorology, and astronomy often involves natural experiments. Surveys. Though experiments are really important to scientific inquiry, there is much more to the scientific process. Sometimes the only way to test a hypothesis is to conduct a survey. A scientific survey is a process that involves randomly selecting representative samples from a larger population. Surveys rely on inductive reasoning. Surveys and experiments can work together. A scientist might take a sample of a population and experiment on the sample to find out characteristics of the population. For example, in 1993, the Mississippi and Missouri River basins flooded, resulting in $15 billion of damage and 50 deaths in the upper Midwestern states. These floodwaters appeared to have contaminated private water supplies, such as wells, springs, and cisterns. In 9 states in that region, about 18% of the water supply came from these sources. A survey of water quality was conducted in these 9 states by collecting samples from some of the water supplies and analyzing them. The survey found that many of the water supplies were contaminated with bacteria and fertilizers. The results of this survey had the potential to protect thousands of people from illness. Using the results. After a scientist has experimented or conducted a survey, he must formulate his results and have his work examined by other experts in a peer review process. If his work is accepted, he can communicate his findings to the world so that they can be useful. He might do this through publishing papers in scientific journals, which other scientists read to stay up to date on current research. Scientific work helps us refine our models and advance our understanding of God's creation. At times, scientists test an idea that consistently explains a certain phenomenon. The scientific community calls such an idea a theory. Since theories offer explanations of what we observe, we can think of them as scientific models. They prove their reliability if they are able to make accurate predictions to explain several different bodies of data. Sometimes they can attempt to connect several different phenomena. The relationship between space and time, as described by the theory of relativity, is an example of this. A scientific law is a statement that describes a recognizable, repeating pattern in nature. Laws often take the form of a mathematical equation. Scientific laws are based on observations made under many different conditions. Generally, scientists consider laws to be very reliable statements of science. Examples include Newton's laws of motion, Kepler's laws of planetary motion, and the laws of thermodynamics. You may hear someone say that scientific laws have no known exceptions, but this is not always the case. Newton's law of universal gravitation, for example, has been superseded by Einstein's theory of general relativity. But we still use Newton's law because it remains workable and useful for many situations, even if it lacks the explanatory power of Einstein's later theory. Thinking like a scientist? Right now you are somewhat of an inexperienced chemistry student, but you don't have to stay that way. If you keep an open mind, you can be transformed into a student chemist. The key to becoming one is to learn to think and work like a scientist. This textbook is your guide to help you along the way. To get you started, Take a look at the case studies below of real scientists who made significant breakthroughs. You will see how scientific research leads to more scientific research, and that ideas must be tested and modified to help us better understand our universe. You never know. Maybe God will call you to glorify Him through the work of a scientist. Case Study 1. The Search for a Malaria Vaccine. In 2011-12, the Bill and Melinda Gates Foundation financed the development of a new vaccine for malaria, called RTS-S or Mosquirix. This vaccine includes a chemical found on the surface of malaria parasites that triggers a human immune response to the parasite. Researchers first conducted trials of the vaccine on adults in Gambia, then on children in Mozambique, then on younger African children and infants. Early results of this testing were mixed, but it was a start. The vaccine didn't prevent malaria entirely, but it did reduce severe malaria in children. Although many others still got malaria after the vaccine, those that did had less severe cases. This was likely due to the vaccination. Though Mosquirix is now approved for use, researchers are still trying to improve its effectiveness. For now, Mosquirix is not the cure-all researchers were hoping for, but it is possible that further research will improve the vaccine's effectiveness. Case Study 2, Nanoscience. One of the pioneering fields of science is known as nanoscience, science on the scale of 1/1000th of a meter. Carbon atoms can be linked to form many different substances, like graphite, coal, diamond, and even a soccer ball-shaped molecule called a Buckminster fullerene. In 1991, Sumio Iijima discovered nanotubes, which form by linking carbon atoms or other atoms to make tubes only a few nanometers in diameter, or 1/50,000th that of a human hair. These tubes behave very differently according to their size and shape. Early models predicted how water would behave inside a nanotube, but in a paper published in July 2004, Russian author Alexander Klesnikov and his research group found additional evidence that water in a nanotube will not freeze, even at temperatures of 8 Kelvin, negative 445 degrees Fahrenheit. The team has committed to refining the model of nanotube water behavior and empirically determining its properties. Chapter Review. Chapter Summary. 1.1. Chemistry. Modeling matter. Chemistry is the study of matter, anything that takes up space and has mass, and the changes that it undergoes. The Bible gives us a distinct worldview or perspective to see and interpret all of life, including chemistry. A model is a physical, conceptual, or mathematical representation of some aspect of the world. Chemistry relies on models that explain, describe, or represent what we observe in the universe, though they cannot give us the whole picture. People have been using chemistry for practical purposes since the beginning, though they have not always viewed and studied it the way that we do now. 1.2. Chemistry helps people. A biblical worldview can be summed up by the Bible's account of the creation, fall, and redemption. The creation mandate is God's command to the human race to exercise good and wise dominion over the works of God's hands. Christians can use chemistry to glorify God, to love their neighbors, and to expose error introduced by a naturalistic worldview. A naturalistic worldview relies on man's reasoning, while a biblical worldview relies on God's word. 1.3. Doing chemistry. Scientists answer scientific questions by observing and collecting both qualitative and quantitative data, then using reasoning to explain or describe the data. Scientific inquiry involves asking questions, making hypotheses, collecting data, evaluating hypotheses, drawing conclusions, and having the process reviewed by peers. The scientific process is not limited to controlled experiments, but could also include natural experiments, surveys, and even accidental discoveries. Hypotheses, theories, and laws are all scientific models. Hypotheses and theories explain, while laws describe. The scientific process does not help us discover absolute truth, but instead helps us develop and refine our models of the natural world. Applied science looks for specific applications of science. while pure science explores the natural world to learn new things about the universe. Ethics. Pesticides. Part of exercising good and wise dominion is weighing the consequences of an action. Good and wise dominion keeps in mind that people are valuable because they are made in God's image. For example, during World War II, the chemical DDT was used with great success as an insecticide to control diseases like malaria and typhus. As its use became widespread for agriculture and for disease prevention in the United States, malaria cases plummeted. In some instances, it was applied in amounts much greater than what was needed, but the results were good. Malaria virtually disappeared in the United States. But in 1962, American marine biologist Rachel Carson published a book called Silent Spring, which claimed that animals were being driven to the brink of extinction by DDT. It generated a public outcry against the insecticide. DDT was soon banned, and malaria cases worldwide skyrocketed. Using DDT improperly certainly caused problems, but not using it at all caused even greater problems. Animals are a resource that God has entrusted to us, but God values people's lives more than those of animals. A wise approach to dominion is to seek a balance, saving people's lives while caring for the rest of creation. Now, scientists are bringing back DDT in limited ways, such as by treating mosquito nets with DDT and spraying indoors. They are also exploring other insecticides to control malaria. But the damage has already been done. Good and wise dominion involves planning ahead and examining all the possibilities to save and improve people's lives, often using science.